All right, let's go ahead and get started. I think what you'll find with similarity is it's going to feel really familiar because we have worked on the methods for solving problems that involve similarity earlier in the semester, and I'll mention that here in just a minute. So, two figures are similar, and that's an important word that has a very specific definition. Two figures are similar if they have the same shape but a different size. So, for example, if I were to say we've got this equilateral triangle here, and then I have this other equilateral triangle over here. Those are the same shape, just a different size. Good words for similarity involve like enlarge or reduce. Like if you're using a copy machine to make something that's 50% of the original or 121% of the original. So enlarge and reduce are words that kind of go with similarity and similar figures. Just as a little side note, we talk about similar figures having the same shape and different size. If we have the same shape and the same size, like those two equilateral triangles, we would say that those are congruent because they have the same shape and the same size. We would call them congruent. What we're talking about today, though, is same shape, different size. So we're talking about one thing is either larger or smaller than the other. Now, when we enlarge or reduce, we want to make sure that this new one is proportional to the old one. We don't want to go from an equilateral triangle to a right triangle and say that these two are similar because they're definitely not. Those two are not similar figures. They don't look anything like each other. They don't have the same angle measures. So, two things are similar. They have the same shape, meaning when we enlarge or reduce, we keep the changes in size proportional. And that's a really important word for us because what we're going to do when we solve problems involving similarity is we're going to use proportions. At the beginning, I mentioned that we've worked on the problem solving technique we're going to use today earlier in the semester, and that's true because the very first topic we worked on this semester in section 5.1 was proportions. And then we saw them again when we did pie charts in section 7.1. So my expectation / hope is that you're really comfortable with proportions, and that's really what today's lesson is about as far as solving them goes, is being able to use proportions effectively to find a side length that you're asked for. Before we start setting up proportions, though, I do want to talk about the idea of corresponding parts. When we say that two triangles are similar, we're saying they have the same shape but a different size. And we can see here we have triangle ABC on the left and triangle DEF on the right. And those two triangles are similar. Mostly, we're not going to get out a protractor and measure, but this page kind of tells us they're similar triangles. So we'll trust that these are similar triangles. So these two triangles are similar, meaning they have the same shape, different size. And when two objects are similar, there are going to be parts that correspond to each other. What I mean by that is if we look at these triangles, I've got side AB over here, and that corresponds to side DE. Those, when this triangle got enlarged, going from here to here, AB turned into DE. That's the part that corresponds to that same side in the original or in the pre-image, if you like that word. Similarly, I've got BC down here, which corresponds to EF. And then finally, we would have AC over here that corresponds to DF. The reason that corresponding parts are really important is when we go to set up our proportions, we want to make sure that the relationships we're creating in those proportions are using parts that correspond to each other. So when we set up a ratio of, triangle number 1 over here compared to triangle number 2 over here, we want to make sure that the ratio we're setting up is like, well, if I have AB in the numerator and DE in the denominator of one of my fractions, then I want to make sure to do the same thing with AC better go in the numerator and DF better go in the denominator of the other fraction I set up when I make my proportion. Often it's very easy to see what the corresponding parts are. Sometimes it's not totally obvious, and we'll get a look at both of those types of questions. Does anybody have anything you want to ask about this before we actually look at a similar triangle type of question? Okay. Here's a type of similar triangle question I want to make sure that you're familiar with, comfortable with, and can solve. Um, Given that these two triangles are similar, find DE, which means find the length of side DE and round your answer to the nearest tenth. As I look at this, okay, I'm being asked to find DE, that's this right here. So right away, I know what's really important to me is that corresponding part that is AB over here. So that's really important. Now, how am I going to figure out the length of DE? Well, as I look at these two triangles, I've been given the side lengths of everything in the smaller triangle. In the larger triangle, I've only been given one of the side lengths. Okay, well, what that means is that this side length down here and the side that corresponds to that in the other triangle, side BC, that's going to be an important part of my solving process. This is my link between those two triangles, is that relationship right there. I know that 7 in the small triangle corresponds to 11 in the bigger triangle. And I'm going to use that to set up my proportion. I know I'm going to have 7 over 11. You could do 11 over 7. That would be fine. But because that relationship exists, 7 over 11 is my relationship between these two triangles. And then I'm going to use the idea that, okay, then 7 over 11, my corresponding parts here are 5 and DE. You could call it DE if you want to name the side length. If you're more comfortable or happier just calling it X, that's totally fine. It's the thing we're looking for. Here's a really important part. Like I said, you're probably pretty familiar with proportions, so I don't want to belabor the point. But since we put the smaller triangle in the numerator, we want to make sure we're consistent about that when we set up our other ratio. And so we're going to go 7 is to 11 as 5 is to DE. So if I'm going to set it up with the smaller triangle in the numerator, I have to make sure to do that in the other proportion as well. Once we've got our proportion set up, now we're kind of done with the picture. Something we do a lot, we go from a picture to an equation that we can solve, and that's what we've done here. And just as a reminder, to solve this proportion, we are going to cross multiply. So I'll multiply this way and have 5 times 11 is 55. I'll multiply this way and have 7 times DE is 7 times DE. Oh, I lost my connection for a second. I'll be right back. Okay, 7 times DE. And now the only thing we have to do to get DE by itself is what? What do I have to do to get DE by itself? I know you all know, but seems like a good place for me to ask a question. Perfect, Karina, Stephanie, you're exactly right. We're going to divide on both sides. I'm going to divide by 7 on the right so that those cancel. If I divide by 7 on the right, I also have to divide by 7 on the left. And so what I end up with on the left-hand side is 55 divided by 7, 7.85714. And on the right-hand side, I have DE. So I'm done, except for that one last step where I was told to round this to the nearest tenth. So we'll find the tenths place, look one space to the right, that's 5 or bigger, so we'll round this up to 7.9. So given the information I was given, that these were similar triangles, plus the values that I knew, I was able to find that DE must have a length of 7.9. Are there questions about that before I have you try one? Excellent. Here goes. Those are similar triangles, A, B, C, D, E, F. Your job is to find the length of DF rounded to the nearest hundredth. I'll set up a poll for this one and let you try it. So find the length of DF and round to the nearest hundredth. And this is definitely the type of similarity question you can expect to see in practice problems, on a quiz, or on an exam. My guess is most of you feel pretty comfortable solving a question like this one, but it still doesn't hurt to practice, just to sort of make sure there's no rust hanging around on any of that. We'll go another 30 seconds and then we'll talk about it. And if you want more time or need more time, just let me know. See where we are on this one. Okay, unanimous. Very good. That's a good sign. Please let me know if you do have questions. We'll go ahead and solve this one together. And what we have here is we have that same relationship we had last time. We have 7 on the left and 11 on the right. So the smaller to bigger is 7 over 11. And again, I'm looking for DF here. So the one that I'm looking for is this one. The corresponding part that's really important to me then is that one. And so let's see, I'm looking for DF. I know the 10, I don't know the DF. Since I set this up as small triangle over big triangle, I'm going to do the same thing and set up small triangle over big triangle, and then we'll solve this. To solve it, we're going to cross multiply 11 times 10 and 7 times DF. The only thing left for me to do to get DF by itself is divide by 7 on the right, divide by 7 on the left. These 7's cancel, and I have 110 divided by 7, which is 15.714. And that keeps going. And that's equal to DF. Last thing we need to do here is round to the nearest hundredth. So we'll find the hundredths place. Look one space to the right. That's 4 or lower, so we'll round this down. The length of DF is 15.71. The poll went great. I'm confident in your ability to solve this one, but please let me know if you have any questions. Kind of like what we just looked at, we have a scenario involving similar triangles. And this is something that might feel very familiar from the beginning of the semester. A 3-foot tall dog casts a shadow that's 8 feet long. At the same time, a tree casts a 30-foot long shadow. How tall is the tree? Now, it says these are similar triangles, but I don't see any triangles. So what we're going to do is draw a picture here, and your picture does not have to be a work of art at all. A 3-foot tall dog. So there's my 3-foot tall dog, and I'm going to label it as 3 feet tall. Cast a shadow that's 8 feet long. So that shadow runs along the ground that's 8 feet long. First thought might be, how in the heck is this a triangle? Well, the sunlight's coming down right there, and that's how we get a triangle out of this. When we look at the rest of this question, it says at the same time, so the sun is at the exact same angle in the sky, making the exact same angle with the object. So that's how we end up with similar triangles. A tree casts a 30-foot long shadow. So I have a tree over here, and it casts a 30-foot long shadow. And again, that's how we get the similar triangle. And what I don't know is the height of the tree. So I didn't necessarily have to draw a picture here, but boy, do I find it really helpful. Just take a couple of minutes and sketch it out. And now, okay, I see how I have similar triangles. Now I'm going to set up my proportion. This is the only side I know in the triangle involving the tree, and it corresponds to over here. I have those two shadows correspond to each other. So I have a relationship between these two triangles that is 8 to 30. So I could set up that ratio. And then let's see, the other ratio I'm going to set up here is going to be about this height of the dog, height of the tree, and so that'll be 3 over t. If I put the smaller triangle on top, I need to put the smaller triangle on top. So 8 over 30 is as 3 is to t. And now I can solve this. I'll cross multiply. 3 times 30 is 90. 8 times t is 8t. And the only thing left for me to do, divide by 8 on the right. Divide by 8 on the left. These will cancel, leaving just the t on the right. And on the left, I have 90 divided by 8, which is 11.25. Here I was told to round to the nearest hundredth. This answer already is. So 11.25 feet is the height of that tree. Yeah, how many questions on that one before I have you try one like it? Okay, here goes. A 12-foot tall tree casts a shadow that is 16 feet long. At the same time, a water tower casts a 20-foot long shadow. How tall is the tower? Round this one to the nearest hundredth. I'll set up a poll for this one. Essentially, what the biggest difference here is you're not given a picture right out of the gate. You can draw the picture, then look for the relationships and the similarity between the two triangles. Disregard that last poll that I just got rid of. There we go. So you don't necessarily have to draw a picture for this, but I find it helpful to draw a picture anytime I have an opportunity. Lots of questions in geometry are really hard to do without a picture. And so I think it's a good idea to just be in the habit of taking the time to draw the picture. It often gives us a much better understanding of the work we're doing. And here we're looking at relationships between two triangles that we know to be similar. We'll go another 30 seconds and then talk about this one. If you want more time, just let me know. See where we are? All right, unanimous again. I had a feeling today was going to be a smooth one, and so far, so good. Um, okay, I'm going to draw the picture. So, what I've got here is a 12-foot tree casts a 16-foot shadow, and the sunlight gives me my triangle. And at the same time, there's this water tower over here that I don't know how tall it is, but it casts a 20-foot long shadow. And again, the sunlight gives me my similar triangles, and I want to know how tall is the tower. Okay, so I've got this set up, and again, let's see here. I have this relationship between these two shadows down here. 16 is to 20 as, when I look at my other relationship, small triangle, big triangle, 12 is to t. Now I've got my proportion set up and I can solve. So we'll cross multiply 12 times 20. Can't do that one in my head. 240 is 16 times t. And then we'll divide both sides by 16. 16s cancel on the right. 240 divided by 16 is 15. 15 without the 0.00 would have been a perfectly good answer here. I put the 0.00 on it just so that it would look like all the other answers from this question, rounded to the nearest hundredth. But 15 would be considered correct. 15.00 would also be considered correct here. Any questions on that before we move on to another one? Okay. We've got the same idea going here, except now we have these pentagons that are similar to each other. Your job here is to find BC. So find the length of BC. I'll set up a poll for this one and let you try it. So far, all the similar figures we've worked on have been triangles, but they don't have to be triangles. They can be other shapes, and here we have pentagons, five-sided polygon that has the same shape or different size as the one next to it. It doesn't really change our process at all. I just want to make sure that you see one that's done that doesn't involve triangles, because it doesn't necessarily have to be triangles for two things to be similar. Kind of nice that we basically have one solving approach that's driving us through our day. We'll go another 30 seconds on this one and then talk about it. One thing I'll say is there are different ways to set up your proportion and be correct. You just have to make sure that you're careful with the logic that you're using when you create the relationships. All right, let's take a look at this one. Not unanimous, but awfully close. Definitely strong agreement here. So we'll take a look at it. Let me know if you have questions. So let's see. I'm looking here, and BC is what I'm trying to find, that side right here. So the corresponding part that I'm looking for is over here where that 11 is. So those two parts correspond to each other. And the only value I know in this pentagon on the right is AE over here that has a length of 5. So I need to find a corresponding part for that. And that's going to be this side right here that has a length of 8. All right, so let's see. I know the 8 and the 5 are important. This 11 and the BC are important. And now I need to work to set up my proportion. I tend to just do these left to right, but you could do it differently and still be okay as long as you're consistent with your logic. And here's what I mean by that. I'm going to do this relationship here, 8 is to 5. And what I've done is big pentagon on top, little pentagon on the bottom. I'm going to use that same logic when I set up my other ratio. Big pentagon on top, that's the 11. Little pentagon on the bottom, that's the BC. And what I'm saying here with this proportion is 8 is to 5 as 11 is to BC. That's the relationship I've created in my proportion. If you always prefer to have the smaller of the two similar figures on top, that's okay. You could say, well, I'm going to compare these with the small on top and the bigger on the bottom, and that's okay. Just make sure you're consistent with that and put the smaller on top and the bigger on the bottom. And now you're saying 5 is to 8 as BC is to 11, and you're going the same direction with your logic. Either way, you should wind up with the same answer here. We'll cross multiply. BC times 8 is 5 times 11. And then we'll divide both sides by 8. Those cancel, leaving me just BC. And on the right-hand side, I have 55 divided by 8, 6.875. And I was told to round this one to the nearest tenth. So we'll find the tenths place, look one space to the right, that's 5 or bigger. So we'll round this up to 6.9. So you can set up your proportion in different ways and still arrive at the same answer. That's not to say no matter what you do is going to be okay. And that's true also, Lorraine. If you want to sort of stay within one figure, you can. You just have to be careful. And what Lorraine's suggesting there is you could keep your relationship within one figure and say 8 over 11 is the same as 5 over BC. That would work too. There are a lot of different ways you can do it correctly as long as you're following logic that makes sense. You can't just set it up any old way and have it work. You can't just take those 4 things and put them in any spot and have it work. For example, if you were to say, I'm going to say 5 is to 8 as 11 is to BC, now it's going to go sideways because what you've done there is you've said, okay, small over big equals big over small. Now it won't work out. Correct, Natalie. That's exactly right. It doesn't have to be on the top. It doesn't have to be on the bottom. It just has to be a logical way of doing it. Either small to big, or the way we had it set up the first time, big to small equals big to small. That works. Or the way that Lorraine mentioned it is inside the figure, this piece over this piece corresponds to this piece over this piece. As long as there's logic to it. You can't just randomly throw those 4 things up there and expect it to work. Make sure you're thinking it through. To me, the way that I usually lean in on is going left to right. And so here I would probably have done 8 is to 5 as 11 is to BC. But there are other ways to do it and be correct. Just make sure what you're setting up has a logic to it. Corresponding parts. So far, it's been really easy to see the corresponding parts, but that's not always true. In a figure like this one, where I have these two triangles, but it's not necessarily easy to see where the corresponding parts are. Some of you that are really visual will have no problem at all. You'll be like, yeah, it's obvious. I got this. Others who don't always see things right away, and I can be one of those, I'll admit, it might be a little bit tougher. And so for a picture like this, what you want to sort of focus in on is you can see that this triangle is a right triangle and so is this one. So there's something going on there with the right triangle. Hey, anytime there's a right triangle, there's a hypotenuse. This hypotenuse over here, DE, is going to correspond to this hypotenuse over here, AB. Those two hypotenuses are going to be corresponding parts. Oh, okay. And then now you may be able to look at this and say, if I were to like reflect triangle CDE across this horizontal line, it would go down on the bottom and then I could see how it corresponds really nicely. Maybe you do that, maybe you don't. But then you might think, well, coming off of there, I've got sort of a short vertical line, and that would be this one. So those two correspond to each other. Or you might think, coming off my right angle, I have this really long horizontal line, and that's going to correspond to this really long horizontal line. Sometimes it can be hard to identify the corresponding parts, and it may help to do some sketching on there. I think whenever it's right triangles, the hypotenuse is a great place to start. Each triangle only has one hypotenuse if it's a right triangle. And we can certainly make those. We know those two correspond, and we'll go from there. That's all I'm going to say about this before I let you try it. Given the fact that AB is 12, AC is 22, and CE is 38, I want you to find the length of DE. I'm going to set up a poll for this one. We've talked about the corresponding parts already. I wasn't sure if I was going to just let you go into this totally blind or talk about it first. I think talking about it was probably the right thing. This one we've been given a picture, but we haven't been given a labeled picture. So we have to be careful to make sure to label those side lengths correctly before we try to solve anything. And there may be times where identifying the corresponding parts isn't always easy or obvious. We'll go another 15 seconds on this one and then talk about it. Let me know if you need more time. see where we are on this one. All right, unanimous. Really good day today on the polling. That's fantastic. All right, the first thing I'm going to do here is go ahead and label these side lengths. AB is 12, AC is 22. Well, that's a little goof I can see in my example. We'll go ahead and finish it up, but I'll have to fix that because we all know that the hypotenuse has to be the longest side of a right triangle. So I'm going to have to make sure to fix that up. But we'll go ahead and play along just for the sake of answering this question. One of y'all was going to catch me on that before I got it out, so I made sure to say it first. All right, and then CE is 38, and we're trying to find DE. And so we look at our corresponding parts here, and I've got this hypotenuse and this hypotenuse. So those two go with each other. And then I also have this side length and this side length. And those two I actually know both numbers. And I'll do little to big and have 22 over 38. And that's going to equal, making sure I use some logic and go little to big again, that's going to be 12 over DE. From here, we'll cross multiply and have 12 times 38 is 456. And that's 22 times DE. Next, I'll divide both sides by 22. And 456 divided by 22 is 20.727, and that keeps going. I was supposed to round this one to the nearest hundredth, so we'll find the hundredths place. Look one space to the right, that's 5 or bigger, so we'll round this up to 20.73. As far as the information I was given goes, that's our correct answer here. We have to make sure that the person who wrote the problem doesn't have a typo here in the beginning that makes it not really make sense, but we're okay with the setting up the proportion and solving it part. If not, let me know. Last thing I want to say today, relatively short lesson because there's just not that much content in section 10.3 on similarity, and we've worked on proportions before in section 5.1 and 7.1. So it's not a new idea for us. So the concept of similarity is one that we can cover relatively quickly. When you're working on your homework, number 8C, just to make sure the question is a little bit clear, I'll give you a little bit of a hint that what it's asking you for there is side length DE. So make sure if you have trouble sort of discerning what the question is, that should be helpful. That what it's asking you to find is the length of DE.